Okay, welcome everyone to this continuation of what is algebraic geometry. Today I would like to tell you about symmetric powers in algebraic geometry, and it'll take a while until I get there. And I do this under the term of the Veronese embedding. I have no idea how to pronounce the name. I'm completely slaughtering it. I already slaughtered it, so let's just go for it. The embedding. Let's just call it the symmetric embedding. Symmetric embedding is much easier. And yeah, it's about symmetric powers and how you can use symmetric powers in algebraic geometry. And again, it's kind of nicest formulated in projective land. You will see in a second why, and that's why I will do it in projective land. But there's somehow a non-projective analog, which is not as nice. Anyway, so where can we start? Where should we start? With the most important object in algebraic geometry, the conic section. So if you remember the conic sections, like the things you can pull up with a flashlight. You have a circle, an ellipse, a parabola, and an hyperbola, depending on how you put your flashlight towards the wall, right? So just straight on, you get a circle. A little bit tilted, you should get a an ellipse, and then eventually there should be some breaking point to a parabola, and then you get an hyperbola. Okay, fine, good. We all love them, and remember that they are given by the important thing is that they're given by no. The important thing is that they're fantastic and they're given by, well, just doing a flashlight trick. But the important thing for this video is that they're given by this degree 2 equation, which I made homogeneous because we're doing projective geometry. So originally you had that result as z, and you remember you just throw in the z to make something homogeneous. So here you have a squared, so a times x squared, b times xy, c times y squared, whatever. For example, the circle would be, the classical circle is a is 1, c is 1, and f is 1, and all the others are 0. This counts as a circle. This would be the circle. Fantastic. And you have those terms, and you have x squared, xy, y squared, xz, yz, and z squared. And this is kind of the type of the conic sections. And the kind of observation is now that we kind of have all of these nice terms here turning up. There's 3, and then there's the mixed ones. Fantastic. And this really means if you just turn it around, yeah, you get a linear equation. So instead of saying, okay, a conic is clearly not a linear equation, a conic section, it's a degree 2 equation. But if you fix a point, you do it the other way around. Let's fix a point, and you want to study the condition that some conic contains a point, then this is now linear in the coefficients, right? So the coefficients are just a, b, c, d, e, f, and now the x and y and z are fixed. So this is linear in the coefficient. So there should be a map that makes something linear, yeah, some linear thing, makes it of degree 2. And this is exactly this symmetric embedding, which I will going to show you. So this is kind of the idea. So the conic sections, depending on how you look at them, they're either degree 2 or degree 1. Depends a bit how you look at them. And this motivates kind of the following embedding from projective 2 space, where you have the 3 coordinates, to projective 5 space, where you have the 6 coordinates. The 3 coordinates is the fixing the point. The 6 coordinates are kind of the coefficient type things. So you send points to coefficients, which are just reorder as you send x, y, z to x squared, y squared, z squared, xy, xz, yz. And the image of this map is a famous surface. It's an embedding of the projective space, so that the projective plane into projective 5 space, and if you project that down, you get the so-called Roman surface, which is kind of a famous topic in topology. But anyway, it doesn't matter. So for this video at least. So what I want to do is what I did is I explained how to replace points with coordinates, and this gives you this map from a 3-dimensional space to a 6-dimensional space in this case. And the generalization of this is the following. So it actually is just a map, and you can do it for any d, this embedding, of whatever you start with p to the n, and you get to its d symmetric power. So before I had n is 2 and d is 2. That was the example on the previous slide. So you go from the three-dimensional projective space to its second symmetric power by just sending a point to its symmetric power. And this is exactly how symmetric powers work, if you remember. So for degrees 0 is a bit boring. Degree 1 would be the linear polynomial. So the symmetric polynomials x, let's say, in 3 variables, x1 plus x2 plus x3, symmetric under changing, kind of under permuting the coefficients, not the coefficients, under the permuting the indices. And usually the basis in this space, the linear basis, would be x1, x2, x3. And similarly here, the polynomials that show up, and the linear basis is exactly the image of this map. And that's what you do in general. So you just send a point to its symmetric power, and this is like this idea of sending a point to the coefficients in the sense of the conic sections. And yeah, so, and interesting enough, so you see symmetric powers turning up in algebraic geometry under this type of map. What is really important is the following crucial corollary, which I think of: you take something away from a projective space, let's say infinity, and you would get an affine space. And this is true in general. And the way to prove it is the following. So the way to prove it is to use this embedding. So you do it for the linear case, which is easy, and then you send it to the symmetric power and kind of use this embedding from before. And the corollary I have in mind here is the following: a projective variety minus a zero set of a homogeneous, let's say, non-constant function is affine. So you take something out of a projective variety and you make it affine, or it will be affine. And this is exactly the slogan I was trying to sell in the previous few videos, that kind of projective is the closure of affine, right? So projective is like the closure of affine in a very similar way that if you take, exactly like my picture here, if you take the plane, you take it in your hand, you wrap it up at infinity, you get the Riemann sphere, or the sphere, and from the other way around, this is like this corollary is like the other way around, you take out the point and you get the plane again. And as I said, in order to prove this, use this type of embedding of projective space into its d-symmetric power, where you really just send the coordinates to the corresponding symmetric basis in the sense of so symmetric power. And symmetric power, a reminder here maybe, is just you act by symmetric polynomials on by permutations on the polynomial ring, and the symmetric polynomials are those that are invariant under that action, and the symmetric basis is the corresponding basis of the symmetric power, which is really just obtained by looking at the symmetric polynomials and just write them in taking out the plus signs and just write them in terms of a basis. And this is exactly how this coefficient map here worked, which came from this idea of studying kind of the coefficient map from points on conics to the coefficients. Anyway, I hope you enjoyed this video, and I also hope to see you next time.